Hello, good morning to all. Today I'm here to continue the class. The topic is advanced food packaging. So today is the second part of this class. I start yesterday. I hope that you enjoyed the last session. And for the ones that were not here yesterday, my name is Miguel Cerqueira. I'm a staff researcher in the International Iberian Nanotechnology Laboratory in Portugal, and I'm here to talk about advanced food packaging. Yesterday, I touched some points about the packaging, about the definition of packaging levels, the materials used. I go through glass, plastic, metals, paper, and also in some nanomaterials that can be used in these plastics. And today we'll go through processing technologies, packaging properties, types of packaging, technology to fill and seal, and some emerging packaging technologies such as active packaging, intelligent packaging, and also edible packaging. So this is the program for today. I will remember some of the learning objectives that I presented yesterday. So the idea of this class is for you to understand the reasons why packaging is important in food industry. We talked about this yesterday. Identify the main advantages of using packaging on foods. Identify the materials and processing technology used in food packaging. Some examples. So we'll be able to identify some common examples of food packaging. We call emerging food packaging systems, and be able to identify some of the most suitable advanced package systems for different applications. So there are some points that I talked yesterday, and I will present also today. And in the end of my presentation, I have time for some questions, and I'll try to answer to all during the time that we have. So regarding processing technology, so it's important also to mention that yesterday I speak about different kind of materials that can be used in packaging, but today I'll be mostly focused on plastic. I will also touch in some points about the paper-based packaging, but mostly of the technologies and materials that I will be exploring today is based on plastic or flexible films based on biopolymers that in some cases some people don't call it like a plastic based, but this is the main idea of today. So for the production, and if you are talking about lab scale or industrial scale, we can talk about two different methodologies: by casting or by extrusion. In case of the casting, we are talking about dissolving some of the materials like biopolymers and other compounds in a solvent, adding some additives that are needed, and then dry this solvent. This can be in a mold, or also during a continuous process in a conveyor where the drying step happens, and then we have the dried film in the end, or dried package material in the end. This is based on solubilization of the polymers and then the drying of the solvent. The other possibility, and is one of the most used by the industry, is extrusion. Extrusion is a very big topic that we have different technologies of extrusion, but are mostly based on the applying some temperature. You don't use solvents. You can use it, but most of the cases you don't use solvents, and then you increase the temperature until a temperature that allows the material to melt, and then when it is melted you are able to change the format or change the material to a film, to a tray, to any kind of form. Normally when you are mixing different materials, you can also add additives like nanomaterials. You put it in an extruder where you can make some compounding or master batch, and then you go to other extrusion process when you are a compression molding, injection molding, or blow extrusion. In the case of flexible films for foods, blow extrusion is one of the most used when you are talking about polyethylene and other kind of materials. So these are some of the processing technologies that can be used in this particular case of biopolymers, plastics, and flexible films. I will show you some examples on how the processing can change the way that the additives and other materials are dispersed in the solution. In this case, we explore the use of cellulose nanocrystals. So we obtain these nanocrystals from cellulose, bacterial cellulose, but they can also be for vegetable cellulose. And then we apply to obtain this nanocrystal, can apply different kind of processes. Can be hydrolysis, enzymatic, acid hydrolysis, and then you can have any kind of mechanical treatment to obtain these nanocrystals. And then you add these nanocrystals to the matrix, and you can form flexible films. And we did that in also in cellulose material. So is this kind of scanning electron microscopy images from all cellulose films. So we have bacterial cellulose with cellulose nanocrystals. The idea was to reinforce these materials, trying to improve the mechanical and barrier properties of these films. What we can see here in no sonication with sonication is that when you are doing this producing these solutions and mixing all together, if you don't apply like a sonication process, ultrasound processing, you are not able to disperse these nanocrystals. And when you are not dispersing these nanocrystals, you are the addition of these additives is not giving you any kind of advantages. So this what we saw here is that with sonication, still with high concentrations of cellulose nanocrystals, we are able to disperse, and we don't have the formation of aggregates, as you can see in the figures A2, A3, and A4. And this is also important for the this is in case we produce this by casting, but in case of extrusion, it's also important. When you are adding any kind of additive to during the extrusion process, and then you're producing the compounding or master batch, it's important to know and to understand if your materials are well distributed in the matrix. And this is one of my challenge when you are adding some nanomaterials or additives to these materials. You can see here the X-ray diffraction when we try to correlate the distribution with the crystallinity was not any kind of change. So that is okay. So the distribution is only is a physical distribution, and you don't have any kind of chemical, at least in the crystallinity of the samples. Other example is when you are trying to mix two materials that are not soluble in the same solvent. In this case, we try to make a mixture between carboxyl methyl cellulose, CMC. This is a cellulose derivative very used in the food industry, and also to produce edible films and edible coatings. And we try to improve their properties, mostly barrier and mechanical properties, with lignin. Lignin is a uh, polyphenols is a macromolecule that is constituted by different polyphenols that extract from lignocellulosic materials. And when well purified, we can obtain a very dark material that we can add to these films to improve their properties. We make these tests. We try to obtain solution, and we make a mixture between 50% of water and ethanol, where lignin and CMC are both soluble. But when we are drying, because this was produced by casting, when we dry these materials, we saw that main is plain because the ethanol will dry in a first step, and only then will be dry the water. We have like a formation of micro nanoparticles in the surface. These micro nanoparticles are lignin. So you have like a self-assembly of this molecule during the drying step, and this is because the materials are not compatible. So we saw in the end that the results are okay. So we improved the properties, but we understood that the compatibility of the materials also in this case need to be improved in order to be able to incorporate this lignin in the films and to reach the properties that we want to achieve. These images are scanning electron microscopy images. You can see the different magnifications and with different concentrations of these organosolved lignin. So it's organosolved because it's tracked with ethanol. Other of the examples that I bring today is the incorporation of nanoclay in polysaccharides, polysaccharide-based films. Nanoclay is very known among packaging industry. It's used as a reinforcing agent, and these also have some properties as antimicrobial agent. And what we try here was to study different levels of incorporation of these nanoclays in these films. What we saw, you can see here on your right, some scanning electron microscopy images. We don't have any kind of incorporation. Then we are increasing from 1, 2, 4, 8, and 16% of this cloised 30B, that is a nanoclay. And in your left, you can see this graph that show how the permeability to water vapor and the permeability to oxygen and carbon dioxide change with increasing of this cloised 30B. What you can see here is that in case of water vapor permeability, you have a decrease of the values with increasing concentration of cloised 30B, but for oxygen and carbon dioxide, you have optimized concentration when you are using the lower amount of cloised 30B. And then start to increase a little bit, but still is lower than the material without any kind of nanoclay. This is explained because of the aggregation of nanoclay in the matrix. So also nanoclay needs to be dispersed, and when you increase these concentrations of these materials, we are promoting this aggregation, and then the results that we achieve are not so good as expected. But we are able to decrease these permeabilities depending of the concentrations that we are using. Other of the processing technologies that has been used in the last years is electrodynamic processing. You can see here one video showing the needle and the surface being processed. So is this electrodynamic processing, you can call it electrospinning or electrospray, can be used to make fibers or particles. We here for the packaging materials you are using to make fibers. The idea is to make the functionalization of a surface using this technology. This technology has several advantages. So one of the good things of these technologies is that you not need to use temperature to dry solution. So you have a polymer solution, mostly with some amounts of ethanol or other solvent, but also can use only water. And then you make the spinning. You have a different voltage. You have a potential difference between the needle and the collector, and then you are making the fibers. You produce this kind of perfect Taylor cone, and you are able to produce fibers with that. And you are able to make encapsulation of some compounds here. So you have the fibers encapsulating some compounds. If you have a compound that the temperature is a problem during the processing, this can be a solution to make the functionalization of the films. We did that in different surface. In this case, I'm showing on paper, so we try it on paper, and we compared the paper with nanofibers compared with the casting, and only with the paper. So in this image, you can see. So here you can see the paper. This is the cross section. Here you have the paper with a layer of the ethyl cellulose, that was the polymer that you used to make this coating. This is by casting, and then you have ethyl cellulose by fibers. You can see here. These are the fiber produced above the cellulose membrane. What you saw, so we did that to incorporate some essential oils and to make this cellulose paper antimicrobial. But we also saw that this is possible making this with this approach to decrease the water sensitivity of paper. So as you know, paper is very sensitive to water. And in this particular case, we are able to increase, with casting already increased a lot. That's based on this kind of material that we used. But then with producing of the fibers, we are able to go through 120 degrees of water contact angle. That is a very hydrophobic material in this case. So this is one of the examples of use of electrospinning. Other of the processing technologies that we can use, it is ultrasonic atomization. This ultrasonic atomization is like a spray, the atomization process. This is a machine that we have in the lab that is a benchtop ultrasonic atomizer that we are able to make the functionalization. Also here in the paper, you can see paper, but we are also doing this in other kind of biopolymer-based films. The capability of this spray is to spread very well and to break the droplets of your solution in the surface to make a very uniform thin coating in the surface. You can see here, this is from the company that sells the equipment. You have the needle, you have the liquid inlet, and then you have the input from the ultrasonic generator. This is good. Imagine you have a suspension of nanoparticles or other kind of materials. You are able to make a good dispersion before being spraying. Otherwise, you'll make like a sedimentation process, and it will be difficult to make this spray properly in the surface. We are using this technology for different applications, for packaging, but also for the production of coatings in foods, directly on foods. I will show you in the mostly in the end of the class what is our approach to produce these coatings on fruits. Here you can see the layer by layer technology. This is one of the technologies that has been used since the 90s, I think, where we can produce different layers of materials in the surface. Here they are using glass. You can see that it's by dipping. It's very easy to produce. So with a machine is easier because you don't have to do by hand, and then you have to try it in the surface, and then you make this successively until building different multi-layer systems. You can go through 20, 30 layers. What is important here to understand is that different kind of layers and different layers, important to mention that these layers go to nanoscale. So we are talking about 200, 900 nano coatings. We can improve the properties of several materials. So we can improve the barrier properties, hydrophobicity, we can incorporate some compounds in the layers. So you have different possibilities. I will also share with you some results that we have using this technique in the template and also in some foods using layer by layer technology. But here you can see that is quite easy to make this development. And if you are doing by hand, it's okay. Take more time, but it's possible. Here I show you some results comparing the ultrasonic atomization and the layer by layer technology. So what we try here was to make the functionalization of polylactic acid films with different layers of chitosan and cellulose nanocrystals. So we saw that it's possible to compare based on contact angle for sure, and we are trying to address this with other technologies. We are able to build these different layers. Different contact angles are considered different surface materials. So you have a layer of chitosan, second layer of cellulose nanocrystals, chitosan, and so on until you have 6 layers of different materials. With this, we are able to improve the properties of PLA films, mostly the permeability to oxygen and water vapor. That is very, very interesting for the applications that we are using at this moment. Why they are important? Because of the packaging properties. So is the next topic here. We can discuss the processing conditions and technologies in the end when if you have some doubts. But here I will start to talk a little bit about the properties. As you know, depending on the material that you are using, different properties are needed. So these requirement of the properties are more related with the shelf life of the product and the requirements of your food product. So if you want to increase shelf life, or in very high shelf life in some products where we have some microbial contamination, probably you will need a high barrier material because you need to avoid the presence of oxygen inside your package. If you want something that is to store or to make the transportation of some heavy packs or some heavy fruits, imagine you can go through mechanical properties that will be more important. But in the end, we need to evaluate all of them to select our final packaging. Also important is the migration corrosion of the materials. So all the materials that are in the market need to be certified and need to pass by this migration test, because if you are using different polymers, materials, compounds, you need to ensure sure that these compounds are not migrating for foods and that the consumers are not, and us, we are not eating these compounds. Is what you see here. So normally use different food simulants depending of the food that you are using. So mostly in Europe and United States, they are very similar. So we have 4 to 5 food simulants, I think. And then each food simulant mimics a type of foods. And you go hydrophilic, lipophilic, acidic mediums, oil-based or materials that or foods that have a lot of lipids in their constitution. So depending of the food where you will apply your packaging, you need to make this migration test in different food simulants. We are not using the foods because it will be very difficult to make the quantification and determination of these compounds, because sometimes it's very, very low amount of compound that migrates in a matrix like a matrix from food. So the food simulants help and is easy to make this quantification. You can see here equipment used for the mechanical properties to make some stress tests. And here is like an image exemplification of our system to make the permeation of make a barrier test of the film. So you put the film, and then you have the testing gas, and you have the amount of gas that passed through, and you have to make the quantification. Depending of the company that is selling this equipment, you can have different approaches to make the measurements of the barrier properties. I will talk a little bit later about this. So permeability is in fact one of the most important aspects in when you are talking about pre-measured packaging foods. So the permeability will change and influence the way that the water is. So imagine if you have a product that with a high amount of water and you want to avoid dehydration. So if you have a very permeable packaging, your food will dry, and this is a problem because change organoleptic properties, lost their weight, so they have this kind of problems. But also the oxygen is a problem. In some packaging materials where you use a vacuum or modified atmosphere packaging, you want to reduce the permeation of oxygen from atmosphere for the foods. So the permeability to oxygen is also very, very important. And so this is the kind of things that you need to do for all the packaging materials. Maybe some of them are not needed if you are talking about secondary or tertiary packaging, but for primary packaging, you need for sure to make these measurements. This permeability is influenced by the permeation process, that is the mass transfer phenomenon that occurs when a molecule passes through a material or membrane from an area high concentration to an area of low concentration. In this case, is the problem of oxygen. If you have a lot of oxygen in the atmosphere and inside your packaging you have a very low concentration, you have this kind of change or phenomenon from the migration or permeation of the oxygen. You have the diffusion that is related with the movement of molecules within the material, and it's caused by the concentration difference. So here Diffusion is related with the different molecules and different materials that you are using, and because of that, depending of the material that you are using, you will have different diffusion coefficients. So this will change the permeability of the materials and absorption. So it's also important the surface of your material and the way that it interacts with the molecules, and will change also the permeability of the packaging material. So there's a lot of uh, questions here and a lot of coefficients that you need to consider to determine the permeability of a packaging. Here, this image can show you more visual how it works. You have the permeation, or absorption, and you have the um, diffusion of the material. One of the important facts here is the thickness of the material. So it's easy to understand that higher thickness will go through higher permeability if you are using the same material and same matrix and components. What normally is we do is make a normalization with the thickness to have like a standard, and then we will not be influenced when you are comparing materials by the thickness. But by the industry, this is not the most used method. So normally they are using very similar thicknesses. So they compare the gas transfer rates of the materials and don't do the normalization with the thickness. So different approaches, different ways, but the important is to measure the permeability and be able to compare it and to understand if they will be enough to reach the needs of your food products. Mechanical properties are also very important. These are two of the the properties that we measure. They are only with one measurement. You can have the tensile strength and elongation at break. Tensile strength is the stress needed to break to break a sample. Elongation at break is the strain on a sample when it breaks. Um, so we can have it. You can see here in these graphs. In this case, the tensile strength, you have the stress. Sample breaks. You can have a value here in Pascal, and then you have elongation, that is the beginning or the width of the sample, and then it start to elongate, and when it breaks, you can convert this in a percentage, and this gives us some idea of the mechanical properties of of your packaging materials. But there are other properties that you can measure related with mechanical properties. So you can make um, perforation tests, sealing tests. So depending of the packaging, you can have a very big number of tests to understand the mechanical behavior of your packaging. And that normally is adopted by the industry depending of their requirements. For us, as a researcher and trying to improve these properties, normally we start by these two: tensile strain, elongation and break, and then we go through other properties if is needed for this specific packaging. Other of the important properties, there are the thermal properties of materials. As I explained before, during the processing, we increase the temperature of the of the materials to when you are doing extrusion, we increase the temperature of the materials to go through the melting temperature. This melting temperature is very important because this is the temperature at which the polymer chains fall out of their crystal structures and become a deserter liquid. This allows us to have a liquid that can be molded or changed and then is processed. Other of the properties that have the very similar behavior is the gas transition temperature. That is associated with systems mobility and is mostly related with the amorphous part of the material. So if you have a semi-crystalline material, we have to be aware that you'll have a glass transition temperature and also a melting temperature. And with that, we need to identify the conditions that they need to be processed. So if you are using extrusion, or you need temperature to maintain the reliability of your packaging, or you have some kind of temperature processing during after the packaging your food. So these thermal properties are quite important in polymer science, and also during the processing of these packaging materials that need to be determined. If you are using casting solvent, um, is not so important, because the important is to be that materials are solubilized in the solvent and then you dry it. So here the thermal properties are not so important, but normally if you go to the industry and you are using extrusion, normally you have to make these determinations. I can give you an example. We are involved in the project where we are using some active compounds. So we are adding additives to a plastics, to a polyethylene. And now, in the end, we are in the industrial tests, and the company has some problems with the sealing. So this layer, this polyethylene is the inner layer, so it's in contact with food, so it's active. I will talk a little bit more about active packaging in the end. And this active layer is in contact with foods, and due to this also is the part that will be sealed by temperature sealing. And I also talk about sealing later on. So this sealing is use the temperature to close the packaging, and they have some problems with that, because we are studying right now. We don't know why it's happening, that the active compound that we are adding to the matrix is changing the way that is being melted, so it's changing as well the way that is being sealed. So now we are trying to optimize the sealing conditions that are different from the previous ones, only using the polyethylene. So this is one of the things that we need to consider when you are using and we are working with polymers and with packaging, in this case plastic based. Other of the properties that is quite important is the optical properties, so the color and the opacity or transmittance of the films. As you know, as consumers, we like to see the food that we are buying. So in most of the case, and that is because also the plastic is very well accepted by the consumers and by the industries, because you are able to see, in most of the cases, you are able to see the foods inside. And that can be a problem in some cases, and for other materials like paper or metals. But in the case of plastics, this is quite easy to achieve. So most of the plastics are transparent. This can bring some problems. One of the problems is the incidence of light in some foods. As you know, some of the foods can suffer some oxidation and change the color with the incidence of light, and degrade in some point with the light. So the idea and what some of the developments have been, some of the developments that have been presented in these last years, is the use of some blockers, light blockers, depending of the light wave that you are trying to achieve. And then with that, we can decrease the oxidation of some compounds. This is the same for the glass. So some of the glass has different colors because they are trying to reduce the incidence of light inside of the products. Is the same from the plastics, but is also one of the properties that need to be determined. The color, in fact, when you are using some biopolymers, is one of the problems, because some of them are based on natural compounds, and some of them, depending on the purification, can also have some color in their composition, and that should be considered during the production of this biopolymer based packaging. So this is related to the properties, and I bring me to the type of the packaging that we normally use. So we have the bag or the sack. Mostly of them are based on plastic or paper. So they are performing most of the basic functions of packaging, such containment, protection, and communication with the lowest cost. So is one of the points that I present you yesterday, where the price of these materials like plastic and uh, mostly plastic and paper are very cheap, so they are mostly used in for this kind of applications. So related with definitions, a flexible container which is open at one end is called as a bag, and a bag holding more than 20 kilograms are called a sack. So this is kind of related to mechanical properties and definition between a bag or a sack. So you have also the bottling. Um, the bottling equipment includes different, each are different from each other, and can be glass bottles and also different plastics with different shapes. And in this process, there are different steps involved, like cleaning, filling, close, labeling, and collection and packaging for the shipment. So there is very automated equipment for doing this in the beverage and other kind of uh, drinks, where they do this in at a level of very huge amount of liters per day. Related to paperboard and the production of, if you remember, the difference between paper and paperboard is the thickness and the application. In this case, the paperboard is mostly used as secondary packaging, and you can see here the image where they are closing, the way that is closed the paperboard, and then you have to fill it with different primary packaging that you are trying to ship, or in some cases some foods that are unpacked. This is a machine where you can see here this machine used for this kind of don't do it by hand but doing automatically. You can handling paper liners, recording codes, and inserting flyers in this kind of other kind of equipments. Um, Other of the important steps during the packaging process is fill and seal. So fill, we understand that. So in this case, I'm showing how we can fill, and several steps are filling a tray with some foods. You can see like meat, fish, in some cases already some fruits or vegetables, like in this kind of package. And what normally happens is that you have the film in point one, and then it's going to be thermoformed to be a tray, and then you have the incorporation of your product, and that can be automatically or manual. And then you have the outer film that will be in the surface of your package. And then you have the thermal sealing. Here you have to thermal seal the film, transparent film mostly, with this tray that normally is not transparent, is totally opaque. And this sealing is very important. It's very important because will be you'll guarantee that you have a barrier and that your package is very well closed, and needs to be strong enough to guarantee that is close to be shipped and go to the retailers. But in the end, we need to be easy to open. So this is kind of, because when you receive it at home, you need to open the plastic up this tray. And also because during this processing, and I will talk about this, you can do modified atmosphere packaging or a vacuum process. So they are performed during this process, during the packaging, and during the filling, and then you need to remove all the gases and then make the film and make the vacuum and make the sealing, or the modified atmospheric packaging, where you have to remove all the gases and then put your mixture that you want to use. And this is doing this process. During the filling, you have different materials that you want to fill. You can fill liquids or solids, and so the filling can be adapted for this kind of products. And depending on that, and depending on the equipment and the viscosity of the liquid, or the way that you are trying to seal to sell the product, you have vacuum, constant volume, gravity, pressure, and also volumetric weight and counting. So this is adapted for the product that companies are selling, and also the requirements from the industry. In the vacuum, is mentioned as one of the cleanest and most economical way to handle many products, and these advantages of avoiding defective bottles. You can see here a machine, you have the vacuum pump, supply tank, and then you are pumping with the vacuum and filling the bottle. Um, the top of the bottle contacts the seal ring, and immediately air is drawn from the container through the vacuum system. So this vacuum system is very used in filling liquids, but can also be used for filling some solids. The gravity, that is well understood how it works, um, is especially suitable for highly foaming products or thicker. So you have very thick products, you can use this kind of way of filling your package. And you have this kind of machine, and you have a supply tank that is elevated above the filling tube, and then you start to fill all your packaging with this kind of processing technology. In the case of the solids, the volumetric approach, where you have this kind of technology, you can have vacuum again, by flask, or by auger filler. So they are different equipments that allow you to fill your packaging with solids by way that is where the basic principle is to divide the supply of the protein to a main feed and fine feed above the waiting head. So we have to put all together here and then start dividing. And what they do is in the first stage, the bulk and the fine feed are operating to fill the waiting pan until about 89% of the required material. And then when this is reached, the bulk feed stops and the dribble feeds continue until the exact balance is reached. So it's two-step and the too fast the process. We go to 90% and then we start filling more slowly. Regarding the sealers, as I mentioned, can bring you some are very interesting because so you also can use some glues that are allowed for food applications, but each sealers avoid using any kind of glue. So you're using only the properties or properties of the materials to be able to make the sealing. So you have to provide heat to the interfaces, pressure to bring them intimately in contact, and completely held, and all within a acceptable time of period. So this combination will allow to make a very good packaging, a close packaging. There is a great variety of heat sealers, which are designed on different principles and different capacities depending of your product. This is very similar to the image that you showed before. So you have the product discharge and the sealing process. And here, when they are being sealed, you can be sealed in vacuum, in the standard atmosphere, so it is normal atmosphere, or in modified and inert gas atmosphere. So that is a modified atmosphere packaging. So this is something that companies need to select, because these are different prices depending of if you are using vacuum or modified atmosphere packaging. There are some examples of the products that are in the market, small, bigger ones, and they are adapted to be used for vacuum. In the case of vacuum, there are 4 types of vacuum machines: nozzle, chamber, skin, and thermoforming type. So, and for this case, you also have different packaging materials. And in this case, the vacuum is created to reduce oxygen percentage in the package to increase the shelf life. So that is clear. So we avoid or reduce the amount of oxygen, and with that, we're reducing the microbial growth and also oxidation and degradation process. So these are some of the values and how it works: vacuum pump, the vacuum pack, and then you have this inside the chamber, and then you have like this skin packaging adapted to the foods. This is other kind of type of machine. So you put all together inside, and then you have the gases being outside by here, and the sealing plate that is pressed and then is sealed by heat. So this is the way that they are doing that in the industry. Regarding the modified atmospheric package is also very interesting, as I mentioned. before. So oxygen is a molecule that is present in microbial growth and also several oxidative processes. So if you are able to reduce it in some products, we are also able to increase the shelf life. So it's associated with respiration oxidation. So, and we also know that carbon dioxide in high concentrations is a natural bacteriostatic. So mostly for the aerobic microorganism. If you have an aerobic microorganism, carbon dioxide can be a problem. And because of that, normally in this modified atmosphere packaging, around 1 to 2% of oxygen is maintained inside to avoid anaerobic growth. Because if they are strict anaerobic, they will not be able to grow in these concentrations with still low concentration of oxygen. So, and then this carbon dioxide is mixed with inert gas. In this case, can be nitrogen, and this nitrogen used to make this process. Most of the packaging materials are using modified atmospheric packaging for everything other than produce most have good barrier partners to all the three gases. So what this means is that when you are using modified atmospheric packaging, you need to guarantee that your material or your packaging has a very low permeability to these gases. So imagine that you don't have oxygen inside your package, but your material is very permeable to oxygen. Will be the permeation of oxygen of the atmosphere to inside the packaging, and then this modified atmosphere packaging will be changed. So we have to have very high barrier materials in this case in this type of products. So right now I will talk about emerging packaging technologies, about active packaging, intelligent packaging, and edible packaging. For now, I will do a very small break, and then I will come back with this topic.